Okay, thank you, Kim. So I've got quite a lot in this presentation, so we'll go a little bit fast, but if you have questions, I hope to follow up on that. So I think, the key message is that we have to accept that Portland cements are going to continue to dominate. They're the only materials that can be made on large scale. And the most realistic option to reduce CO2 and extend resources is to introduce more SEMs. And of course, the problem we have is that the SEMs we've been using in the past, like slag and fly ash, are even today available in quite limited amounts. And because these come from very CO2 intensive processes, these are basically going to disappear in the next 10 to 20 years. I mean, the plan is to really phase out coal and find alternative methods to reduce iron from iron ore, and of course recycle steel. And so these are just going to go down and down. And we have various things up here, and the message is that the amounts aren't very large. Somebody asked a question about things like basalts and tuffs. The problem is that they're not available in that many places. What we do have, of course, is limestone, but when we introduce high additions of limestone, it just becomes a diluent. So the real game changer in this regard can be clays that we can calcine. And, so basically to summarize that, I think we have to face there's no magic solution. What is really, really interesting is this synergistic reaction between calcined clay and limestone, which can allow you to go to high levels of substitution, which is behind the technology we call LC3. And basically what LC3 is, you use this combination of calcined clay and limestone, a bit like what Jesper showed, and you can have very different levels of addition. So Jesper was talking about LC365, basically, which would be allowed under the past European standard. Now with a new European standard, we can go to 50%, and we actually know we can get good properties even with 40% clinker. And if you have a good quality clay with a large content of kaolinite, again, you get a very small reduction at 1 day, but by 7 days, you have a higher strength. So you have 50% less clinker, 40% less CO2. This takes into account the energy to calcine the clay, similar strength, and some properties like chloride resistance and resistance to alkali silica reaction are greatly improved. I'll come back to that. So our LC3 project, we've really combined teams from 3 main areas, from EPFL in Switzerland, from India, where we have a few of the IITs involved, and from Cuba with Fernando Martirena. And we have now 2 what we call technical resource centers. So these are aimed at providing practical advice for people on how to implement this calcination. So the first step, of course, in implementing this in field is to really identify the right kinds of clays. And the important thing for getting the best reaction is to have kaolinitic clays. Now, we've seen earlier on in the sessions today that you can get not bad reactivity with the other clay types, but you will get far, far better reactivity with kaolinite types. So, if you have kaolinite types available, this is really the place to go. And this is because kaolin are what's called one-to-one clays. They have a layer of silica and a layer of alumina, which means both the silica and the alumina can participate in the reaction. And this brings about lots of benefits, as was shown in earlier presentations, as in the one from Oregon State and the one by Mike Thomas. So we've now tested more than 70 clays from all around the world. People said to us, clays are so variable. This is true. They have many different minerals present. You can quite simply measure the kaolinite content by looking at the weight loss between about 400 and 600. And when we have studied this vast data set of clays, what we basically see is that the strength development correlates very closely with the content of the kaolinite. And these red lines on the graph here show the reference strength of the plain Portland cement. So you can see at 28 days, if you have a kaolinite content of only 40% or so, you can match the strength of your reference Portland cement. So just summarizing that, we kind of say the ideal kaolin-like content is 40 to 60%. If you have higher contents, then the benefit is you could just put in more limestone, because if we go back to this graph here, you see that there's really very little extra gain going above about 60%. So you may as well put in more limestone. You get even more reduction in CO2, and it's even cheaper, and you can improve still further your rheology. And if you have lower contents, particularly quartz is often a mineral that's present, then it's quite a good idea to look at separating it out. So we saw the presentation this morning from Penn State. I think from a practical point of view, using surfactants is going to turn out to be a little bit expensive, but even dry separation, you can get pretty good enrichment. So this is just another way of translating this kaolin-like content to a rough idea of the amount of alumina. And the really good news is that these clays are super abundant, really just about everywhere. So these are two kaolin-like maps for the topsoil, the subsoil. Anywhere you see this kind of yellowy orange color in either map, then you will have very suitable clays. And what's really cool is that the best abundance is in those areas of the world where the demand for cement is really going up. So Africa, notably, Latin America, India, Southeast Asia. And so really you've got these ideal raw materials in exactly the right place you need them. So, and often they're available as waste. We had a nice presentation this morning to show how they could be waste from getting aggregates. This is another example. And also Imeris showed how you can have over or underburden clays, which are very suitable. This is a similar example coming from India. So when we want to produce LC3, I think we have to bear in mind that, LC3 is the idea that we take the three ingredients. We take the calcined clay with the clinker, the limestone, and of course the gypsum, and we grind them all together in the cement plant. But we can also do it another way, which is probably more suited to the North American market. We can take the additional SEMs, we can take the calcined clay with limestone, and it's important to add a little bit of gypsum because it's important to adjust the sulfate. And then that is a sort of package ready to go that can be added at the concrete level. So it's important to see that we have these two ways of doing things. And at the end of the day, it doesn't really make much difference. But the processes are still the same. You need to find suitable clay. You need to process the clay and then calcine it. So when we come to the calcination of the clay, even though the dehydroxylation takes place between 400 and 600, we find that the ideal range for calcination is more in the range from 700 to 850. And that's because we increase the disorder in the metakaolin structure, and that increase in disorder makes it more reactive. If you start going above about 850, then what you find is you tend to start getting agglomeration, the surface area goes down, and that decreases the reactivity. And if you go very high, if you go above 950, then really it's a disaster because you just get recrystallization, and then the reactivity is almost non-existent. So many people say, well, can we use fire-clayed bricks? Well, the answer is really no, because generally fire-clayed bricks have gone up to a temperature more in the range 950. And this just shows this agglomeration process. So calcination methods, Jesper already said, you can use rotary kiln, you can use flash calcination. There are various advantages or disadvantages. We found, like he did, that really it makes very little difference to the reactivity. Of course, the benefits of a rotary kiln, you can even use existing kilns. Recently, in a country I can't tell you, we actually shut down the clinker production, and within 4 hours, we were able to start calcining clay. So this just shows you with absolutely no adjustment, you can use the same equipment. Of course, if you want to make a production on a permanent basis, then it makes much more sense to get a separate calciner. And this can either be rotary kiln or flash calciner according to your preference. So this was the first production of calcined clay we made in 2013 in Cuba. Just to emphasize the point, this was by no means a sophisticated operation. This was quite an old kiln, and yet they could successfully calcine the clay. They could grind it and put it into bags. They could take it to the local block making plant, give it to the operatives with absolutely no additional training. They could use it on a one-to-one replacement basis, and the product had absolutely good strength for the application. Here you see we're making nice flowable concrete. This is made with available admixtures. Those slightly increased, but as Jesper said, now we have many new admixtures coming online, and I think there's really no problem of workability in the long term. So this is a house that was built in Cuba with the blocks made of LC3 and also this rendering material made of LC3. And for applications like rendering, it seems to have very good qualities of very smooth application, resisting any bleeding or segregation. Our second production was in India. We had a little bit more sophisticated apparatus here, but again, we could make blocks. We built this house, which is almost entirely built of LC3, and we could calculate the savings of about 14 tons of CO2 compared to existing solutions. Moving to, more implanted industrial processes, one of the first permanent industrial processes in Ivory Coast, where they've installed this double shaft rotary kiln, which enables you to adjust the operating conditions according to the moisture content of your clay. And this is often important because according to the weather you have, whether it's rainy or dry, the moisture of the content of the clay can vary a lot. And it's quite convenient to have this kind of design because it enables you to operate on the best conditions with the minimum energy content according to the moisture content. So this is the fully installed kiln in Ivory Coast. And many people are asking questions about color. And I really want to stress that really color is not an issue when you're in industrial production. This is a technology that's very well known in the brick industry. If you've ever bought bricks for your house, you know you can get different color bricks. And this technology can be transposed perfectly to calcined clay. So this is the raw clay in Ivory Coast. If you don't apply the color control, you have a red color, but you can apply this very easy color control and you get a gray color. And this gray color, of course, matches very well the color of normal gray cement. So I really want to stress that color is absolutely not an issue. This is quite difficult to do in the laboratory, but on an industrial scale, it's very easy. So in terms of performance, if we compare to existing substitution materials like slag and fly ash, we see that in the long term, these mixtures, and we did two types of mixtures. We did binary mixtures with 30% of the SEM, and then we did these ternary mixtures with the SEM and with the fly ash. You can see at long term, they're all pretty similar, but at early ages, the calcined clays always have the highest performance. And here, when we're into blending in the lab, we do have lower strengths at 1 day, but again, in an industrial context where you can adjust your particle size distribution, you can maybe use separate grinding for the clinker part and then the calcined clay and the limestone part. We have several examples from real life situations where we can get the same strength even at 1 day. So the key advantages we found are chloride resistance. This was already talked about this morning, and alkali-silica reaction. This shows the results of those different mixtures in terms of chloride ingress. So, this is the OPC with very big penetration. This is the one with slag, which is quite a lot better. This is the one with fly ash, which is better again, but the best is the calcined clay and the calcined clay with limestone. And although Yuvraj talked this morning about tortuosity, I'd like to emphasize that it's not really a geometric effect of tortuosity. Our research has really shown that it's much more a direct interaction of the chloride ions with the CSH product. So, don't get this idea that we're forming this very, very different microstructure. It's really the same microstructure, but this slowing down of chloride transport due to interaction with the surface of the clay. And because the materials are much more fast reacting, it's much easier to get this improvement in performance in the field. So these are resistivity tests. You see the LC3 example is very, very similar in the field and in the lab, whereas fly ash, we don't get as good performance in the field as in the lab because the curing is more difficult. And this is some real exposure sites that have been out on an exposure site in Cuba. This is quite low strength concrete, only 20 MPa, but the penetration in the LC3 content is less than half of the OPC. Alkali silica reaction, very good because it brings down the alkalinity, but also because it releases alumina to the solution. And we know that a small amount of alumina in solution can drastically decrease the dissolution of silica. Now, the two things people go on about are workability. I've shown you many examples, and Jesper showed a nice example of how the workability can be really good. And in fact, if you want to self-compacting concrete, you actually may have a lower overall cost of admixtures because it's so resistant to any segregation or bleeding, you don't have to add any viscosifying agents. Carbonation is faster, but as Jesper said, it's very much in the same range as what you get with existing SCMs like fly ash and slag. So the potential for CO2 reduction, of course, the potential on the level of the actual cement depends on the conditions of calcination, the proximity of the clay. We've shown that it can be up to 40%. What I'm more interested in is what it can do on a worldwide basis, because that's what we're really confronting with this climate crisis here. And here we see the average level of cement substitution amongst the companies who are members of the Global Cement and Concrete Association. And we see that in the last 10 years, this level of substitution has stagnated at around 20% because it takes also account of the 40% the 5% gypsum here. Now, I think most people agree that from a technical basis, we could very easily go to an average substitution level of 40%. And if we did that with a mixture of calcined clay and limestone, we would save 400 million tons of CO2 per year. That's huge. That's like 1% of all global CO2 emissions. And that's on a very conservative estimate because that is saying 40% substitution. And our recent work has really shown that probably we could go to double that. So probably we could go to 800 million tons of CO2 a year. I don't think there's any other single technology in the cement and concrete business that can deliver those kinds of CO2 reductions. So regulations in Europe, we've seen this change in the standard this year, which allows now to go down to a clinker content of 50%. In North America, we do have, and much of Latin America, we do have already ASTM 595, which would allow LC 350. But, this is really not being used. Really, people are using additions at the concrete level, which would favor LC2. Finally, on the finances, I mean, everybody talks about green products having a green premium, but in this case, you get what's apparently called a green discount, that the green product is cheaper to make than the traditional product. So this is a report you can download on our website, lc3.ch. And this demonstrates for a typical case of production in an integrated plant where you're producing the clinker, you can get savings around 20%. What's really, really interesting is if you have a grinding plant, and that's the situation for much of Africa, where demand is going to be the biggest, increasing the most in the coming decades. And there you can get really huge savings. And in fact, the clinker price here is way below the clinker price that many people are actually paying. So very, very attractive from all points of view. So steps to industrialization: clay identification, clay testing, economic feasibility, mortar testing, concrete testing. These are all the stages that you need to go through. And if you need any help on all of this, please contact us. We're now working with more than 40 countries around the world, and I hope to see many more commercial productions coming online in the next 1 or 2 years. So just to conclude, I think we have to see that this is a really, really important technology to lower global CO2 emissions. And if you're interested to know more, please come to our conference. So next July, we'll be having this conference in Lausanne. The next calcined clay conference was due to be in Beijing, but that's been postponed. So in the interim, we've put in this one in July 2022. And thank you. And I hope I haven't gone too much over time, Kim.
You did great, Karen. Get a number of questions. Let's see. So why don't I start with Karthik Obla has a question. How easy is it to produce LC3 concrete at a concrete plant? Could you use limestone powder, calcined clay that is available commercially? The addition of gypsum, though, may not be permitted by standards. So could you blend this, like as you were saying, in the US at a plant versus selling it as a product?
Yeah, I think you can. I mean, there's various possibilities. I mean, the presenter from Oregon State this morning showed that you could use an already existing Portland limestone cement, which is a good solution, just add the calcined clay. You do need to make sure your gypsum's adjusted. And I don't really know all the rules on that, but, really there needs to be some good sense in this because, this is a huge problem in North America, not just for calcined clays, but for fly ashes. You can easily tip your cement into an undersulfated state, particularly if you use admixtures. And, that's just crazy because then you get all kinds of problems. So, really, this is something that needs to be looked at. I kind of think if it's really only a minor addition of like 2%, then probably it can be allowed, but I'm not sure on that.
Okay, at a batch plant.
But really, what you want somebody to come and put all those ingredients together in the right proportions and with the right particle size distribution, and then just sell that as an addition.
Okay. We've got another question. Kashir Jafari says, great talk. What is the reason or mechanism that calcined clay mixtures show higher strength at early ages compared to other mixtures?
Well, it's just very simple. It's just because the calcined clay is way more reactive than things like fly ash and slag. And the answer for that is that, calcined fly ash and slag, they're kind of glassy materials, so they only can react on the surface. Whereas a clay, it's a layer structure, so you've got a way higher surface area that can react. And because it's not a glass, it doesn't have to kind of dissolve in the same way. It's really more a disruptive structure, and all of these contribute to a much higher reactivity.
I'll just ask this last question, then you'll have to answer the others in the Q&A. Chris Bieber asks, he asks about ASR and the benefits, and it was before you got to that in your slides. But he asked specifically then also, do you see any benefits in reduced efflorescence?
Yeah, we never get any efflorescence. You've got great water retention here. So the movement of water in these systems is just completely reduced. So we've never seen any problems with efflorescence. We haven't done an extremely severe test. We would need to do that to check, but I think it would be absolutely great because you're vastly reducing the amount of mobile calcium and everything.
Great.